Hello everyone, welcome to this tutorial. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to extract the water body and how to calculate the water temperature using Landsat-8 and 9 in the Google Earth Engine platform. This tutorial is very helpful if you want to use the temperature for the water quality analysis. At the end of this tutorial, you will be able to plot or make a multi-temporal plot showing the water temperature dynamics through a year and months. Okay, make a new notebook in the Colab environment and start with importing essential libraries belongs to Google Earth Engine platform. So let's start with EE library and then GEE map. Import xarray as XR. Then install the XEE. The XEE is one of the newest libraries developed by the Google community, allowing us to combine Earth Engine image collection with xarray data structure. Let's run the first cell. As you can see, the Colab is making connection to the server first, and then the importing process started. If you faced with any challenge in this tutorial, feel free to find the code example below this video in the description box and you can compare my code with yours. So if a still problem exists, then you can reach me out on my YouTube channel. So as you can see, the library is successfully imported or installed. Let's clear the outputs. The next step is establishing the connection between Colab environment and Google Earth Engine. Use the Earth Engine library authentication first and initialization or initialize. So enter the project ID. Go to the code editor environment, upper right, account information, then project info. Every user has a unique cloud project. Copy and paste, just like this. The next argument, opturl. Go to the XEE library, XEE GitHub page. If you search about the Google Earth Engine and XEE, you will find a GitHub address. There is a detailed instruction about the XEE and how to use it in the Earth Engine. Scroll down, you will find the opturl address. Let's copy and paste into the code, just like that. Let's run the cell. Now Colab asking permission to get access to your Earth Engine account. Select the associated account, then continue and continue. So now we are establishing a connection between Colab and Google Earth Engine platform. So everything settled. From now on, we can use Earth Engine functions, programming techniques, and data catalog in the Colab environment under Python standard. So, in the first step, we need to identify the region of interest, make a new variable, then from GEE map, call the map function with a satellite base map. Let's run the map. Now you have a user interface with the drawing tools allowing you to select the region of interest without any challenge. In this tutorial, it is important to select a water body. I prefer to select a reservoir in the southwest of Iran. This tutorial can be used for all around the world and all water bodies, not limited to a single location or actually not limited to only one reservoir. This is extendable to all surface water bodies. Okay, now we have a reservoir in the southwest of Iran, as you can see here, and now I want to actually calculate the water temperature in this area. So draw a rectangle like this, and then we need to have the rectangle as a variable, ROI, region of interest. So from map, select the last feature, just like that. Convert it into a geometry format. Let's run. So the ROI is created and including the coordinates of the rectangle, just like that. The next step related to calling Landsat images. I need to use Landsat-8 and 9 together. Go to the code editor environment, and here you can find the Landsat collection 2 level 2 data. Landsat-8 collection 2 level 2. This product is atmospherically and radiometrically or even geometrically corrected. So no more pre-processing needed, just this is ready to use, import and start the analysis. Landsat-8 collection 2 level 2. Let's import it and go to the page and find the collection snippet. So in the Colab environment, a new variable L8 created. So make a tuple and paste the snippet. So we need to define a spatial and temporal filter that filter date. For example, I'm gonna study the water temperature for 2024 and 25, but 25 not considered. Filter bounds, call those satellite images covering the region of interest. Okay, if you go to the bands, there are different information about the bands, spatial resolution, spectral resolution, and etc. So in the first step, I need to mask the cloud cover in each data first, and then separate the water body using NDWI and calculate the temperature using surface temperature. Okay, in the first step, you can see there is a QA pixel band, including the different bits explaining the pixel situation. For example, the cloud, shadow, or cloud, or something like this. So we need a function to handle this process. Okay, for example, the function name here is OLI. The OLI is the Landsat sensor name. So the input for the OLI function, consider it as an image, one image or one feature of Landsat data. So from each input image, I want to select the QA band. QA dot select QA pixel images or pixel image. So it has a bitwise structure, and I need to use a bitwise AND to select the associated bits with the cloud or related parameters. So for example, the bit 1 is a kind of cloud, for example. So cloud number 1 sets to, so from QA band use bitwise and from 1 go to the shift to the left by 1 bit. As you can see, from value 1 we are shifting 1 bit to the left. Select all values not equal to the 0. The second bit is a cirrus band. Cirrus. So QA bitwise and so from value 1 shift to the left by 2 bits, just like this, and select pixels not equal to the 0, and the bit number 3 covering another cloud. So this is, for example, cloud number 2, QA bitwise and so from value 1 shifting to the left by 3 bits, and select all values not equal to the 0. So bit number 4, the shadowy pixels. So here we have shadow variable from QA band. Use bitwise and from value 1 shifting to the left by 4 bits. Select pixels or values not equal to the 0. We need to make a final mask. We need to integrate all these masks together. So using OR operation, we can integrate all of them. Cirrus dot OR again, cloud number 2 dot OR, and shadow. So we have 1, 2, 3, 4 proxies for the cloud. 1, 2, 3, 4. It's okay. So now we have a cloud mask that is applicable on multispectral bands. So here we have the multispectral bands ranging in visible and infrared region. So let's select the multispectral bands from input image. Select all the bands starting with SRB. So then there is a scale and offset to rearrange the input values to the real range of values. So all multispectral bands should be multiplied to the scale first and add to the offset value minus 0.2, just like this. So now we need to calculate the NDWI, normalized difference water index. This index helping us to separate the water and non-water pixels. So from multispectral bands that is already corrected, calculate the normalized relationship between band number 3, green and near infrared, SR band number 5. This is NDWI image. So the normalized difference water index calculated. In this index, values greater than 0.1 referring to the water body. So now we will have a water mask based on NDWI. So in the NDWI, pixels greater than 0.1 should be selected. So at the end, we want to have the temperature for the water bodies. The temperature information already calculated for the band number 10, STB10, showing the surface temperature according to the data description. So land surface temperature equals from input image, select the band number 10. So it's based on a Kelvin, but there is a scale and offset here too. That's multiply a scale that add to the offset 149, just like this. The LSD also here calculated. So we have LSD, water mask, and cloud mask. At the end of the function, we want to have the temperature while it is a temperature only for the water bodies through the water mask, and then we need to remove or get rid of the cloud cover. So update mask, the second mask cloud cover, but dot not should be added to skip the or remove the cloud and keep the true values. So we need to have the properties about or properties describing the date of acquisition. That's properties img and system time start, just like this. So yes, now it's working well. So let's apply the function on each Landsat-8 data available in 2024. OLI applies on Landsat-8. Let's run. As you can see, 44 elements or 44 images available for 2024. In all of the images, as you can see, we have a surface temperature data with date acquisition information or system time start. That LSD only shows the water temperature because it's masked based on the water mask, and also it's already clear from cloud impact. The cloud values turn to the no data in this step. We can apply this function on Landsat-9 data because Landsat-8 and 9, both of them carrying same sensor. So Landsat-9 tier 1 imported here. So another variable here is Landsat-9. Make a tuple again, go to the Landsat-9 information, copy the snippet, and same filters. Filter date for 2024 and 2025. That filter bound your data to the region of interest and apply the OLI function. Let's run L9. 46 elements available by Landsat-9. Each one of them, Landsat-8 and 9, both of them offering temporal frequency with 16 days. But when we combine them or integrate them into a single function, that is single image collection, in that case, the temporal frequency increased to the 8 days. So, meaning that we will have more frequent temperature analysis for the study area. So, the final collection sets to Landsat-8 merged to the Landsat-9. But remember that to sort them based on system time start property, it is really important to have all the Landsat images in a correct temporal order. Let's run. There it is. You have 90 elements. So we are crossing Landsat 8 and 9. So in the next step, I need to convert it into an xarray format using Google Earth Engine using XEE library. So a new variable dataset created called the xr and open dataset function. The input is collection. The engine is the Earth Engine. CRS EPSG 4326. A scale should be 30 meter. The scale is based on a degree. 1 degree 100 kilometer, 0.1 10 kilometer, 1 kilometer 130 meter. Region of interest ROI. So you can see the original format in the Earth Engine is an image collection format where you have a list of features, we have bands, and also the other data structure. But here the data set converted into an xarray format. We have a multi-dimensional array structure. So 1 dimension for time, 1 dimension for longitude, and 1 dimension for latitude. And also here we have the variable that is the surface temperature that's showing the temperature in 3 dimensions, time, lon, and lat. This format is very efficient for the machine learning data analysis. Remember that before further analysis, to sort the data, sort by based on a time first. And also here we have the temperature based on a Kelvin. After applying the scale and factor for the surface temperature, the unit of measurement is Kelvin, and you will have the temperature based on Kelvin. It is hard to interpret when you are using the data based on a Kelvin. You can convert it into a degree Celsius by a constant value, 273.15. So now we are converting the data set into a degree Celsius unit. It is easier for interpretation. So the data set now is ready, and we can make a plot for 1 month, for example. So the input data set here, you can see there are 90 images, and I want to plot, for example, one of the months like July. So here 1 dimension is time. So if I use this cell, I will be able to select based on a spatial and temporal characteristic. Time sets to from the data set called the time and select the month. dt dot month, for example, month number 6, month June selected. Only 6 images available for this month. So select the variable that is surface temperature for band number 10. Let's make a plot then. Let me to make a bigger space for plotting process. So in the plot structure, x-axis sets to longitude, y latitude, called time, and called wrap. How many plots we will have in each row? For example, the 3 is good. Robust sets to the true, that avoids outlier impact on the quality of measurements. Let's run the plots, and here you can see the water body extracted successfully, but you can see we have a huge impact of cloud for most of the time. This is only for one month. We can check it out for different months. For example, in the July, we have a better situation, more number of the data. Instead of 6, we have 8 satellite data, and temperature over the water body in this area varies from 32 to 46. The overestimation for the water body happening in the shorelines or in the coastal areas where the pixels mixing by the water and non-water pixels. So there is a situation here. We need to use some method to fill the existing gaps. So there are various techniques, interpolation technique or aggregation technique, allowing us to fill such gaps. For example, I prefer to test out the rolling method, the roll data sets. It's a kind of moving average. ds.rolling, set a window size. For example, I want to have a 7 days window size. Consider each image as a center and mean periods sets to 1. For every 7 days, I want to calculate the average temperature through the time. So let's check the ds roll. Copy the same code into a new cell. So ds roll this time selected, and let's run. As you can see, most of the gaps filled after the averaging technique, so it's very good and useful. And even we can change the color palette, for example, from existing color palette we can change it into a turbo format. So now it's a little bit better, lower temperature with the darker colors, higher temperatures showing with the lighter colors. So there it is. So as you can see, the water temperature is calculated over this region. We can get a final map using PLT. So before the PLT, it is important to import matplotlib.pyplot as PLT. Now, thanks to the PLT, you will be able to save the final figure. The final figure is, for example, water temperature, PNG format, DPI 360, BB box inches, sets to tight. Let's run. Open the left panel. After a few moments, you will have it. So water temperature is ready. Click on download, and there you go. You will have a high quality map that shows the water temperature over the period of time you want to study. So in the next step, I'm going to show you how to calculate the average of water temperature through the time, and then make a plot or make a graph that shows the average temperature dynamic through a year. It is also easy to do process. So the variable, the smooth temperature or ds roll should be called again. So the ds roll, here we will have the ds average, get the ds roll, calculate the average through the over 2 dimensions, longitude and latitude. ds average. Let's run. So now we have only one dimension, that is time, and for each time the average temperature calculated. So we can convert it into a data frame, to data frame, just like that. And you can see that there is two columns. One of them is temperature and another one is the time format. Make a plot just like this. You can see the temperature dynamics over a year. So it's actually the average temperature in this area ranges from 17 to 35 degrees Celsius in the 2024. So as you actually saw in this tutorial, we easily calculated the temperature of the water body through the time by combination of Landsat 8 and 9 images. If you faced with any challenge in this tutorial, feel free to share your comments on my YouTube channel. I hope you like it as much as I did. Thank you for your attention.